All right, so we are here.
Did you check the size?
Hmm?
Do you have enough room?
Yeah, I'm pretty sure. Yeah, we got about 11 gigabytes left. So that's good for 5 lectures easily. All right, so getting back to system calls and also interrupts. Last time we talked about interrupts already. We talked about how you can use interrupts so that the operating system doesn't need to poll and keep asking an I/O device, are you ready? Or are you ready? Are you ready? Have you received the byte? Have you received the packet? And so on and so forth. So we leave it up to the I/O devices or input/output devices to do their own thing. Only if they have received something or if this transmit buffer is empty and they're ready to transmit some more, they will get the attention of the processor and say, hey, I can do some more work here. What am I supposed to do at this point? And that's the whole concept of hardware interrupts. And the advantages of hardware interrupts is obviously you don't need to do polling anymore. Okay? Because polling really complicate programs a lot, especially in a multitasking type of environment. Multitasking, multi-user environment makes it very hard to use the polling technique because you can only do polling when you have one thing to do. Then you can just keep asking an I/O device, is there anything for me to process, and so on. But when you have multiple things to do, it's really hard to get stuck in a loop to do that. And it's also going to consume CPU power at the same time. So I think that's where we stopped last time. Is that correct? In terms of just the concepts of interrupt handling. The next topic talks about privileges. Okay, in other words, why do we even have a separation of privileges when different programs run? Certain programs can have access to more parts of the system in terms of hardware, and other programs only have very limited access to resources in an in a system. Okay, so this has to go all the way back to the Windows days. Okay, so in early Windows, Windows 3.1 all the way up to Windows 2000, not 2000, Windows Millennium, these are not protected operating systems. I think the later ones have semi-protection, but not full protection. What it means is, in your program as an application, if you choose to go to some random location in memory and decide to, okay, I'm going to change that to some other value, you can do it. Okay, you can go ahead and clobber, any memory location that you want to clobber. And not only that, you can also talk to I/O devices. You can go to I/O location, so and so, and then just decide, I'm just going to spew out something to that particular I/O location. So in the end, what you can do is ended up, messing up the IDE controller. So the IDE controller will send some, random bytes out to the hard drive, and you end up with a much bigger problem, because now your hard drive itself is also going to be corrupted. So obviously that was a bad thing. Okay, we cannot let every program to have the same level of access to the resources in a computer. Is that part okay? Does everybody understand, the necessity of protection? Okay, so the hardware was actually capable of doing protection. Even from the 286 processor on, they were able to do certain types of protection. Software could not keep up with the hardware design. So in other words, Intel designed their processors with the protection mechanisms already. But Microsoft did not actually implement and make use of those features until much, much, much later. Okay. Let me ask you this question. This is a history question. When the 386SX processor first came out, and that was a long time ago, they were still running at 16 megahertz at the time. What was the Windows? What was the version of Windows when the 386SX computers were manufactured?
They have Windows?
They had Windows already, but it was Windows 3.1. Okay, 3.0 or 3.1, and then later on they had 3.11. Windows 3.11 was basically kind of like Windows 98 SE second edition. It's what Windows 3.1 should have been, but instead, they release it as Windows 3.11, and people actually have to pay extra money to get the upgrade from Windows 3.1 to 3.11. But anyway, that's when Windows 3.1 was released, was when the 386 processor was already out, and hardware manufacturers were already using it. The 386 processor has all the protection levels necessary for a modern processor or for a modern operating system. But Microsoft did not put those in until Windows NT was developed. Okay, so software stays behind, in this case, by a long shot. Okay. All right. So now that we know that there are different levels of access to the hardware of the computer, in other words, in Linux, you cannot just say, okay, I want to change location, blah, 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 to some other content. Okay, let's go ahead and write a program to try and do it and see what happens when we try that. Okay. So I'm going to go to my today's folder. This is not really that important, so it's just that I want to write a simple program. So I will say segfault.c because that's what the program is going to do. It's going to cause a segmentation fault, which is just another word to say that you're trying to access a resource that you're not supposed to. Okay. So I'll just go ahead and do something like this. Here's a pointer. I don't even need to declare a pointer. All I have to do is to do something like this. Dereference 0 as a location, and I'm going to change the content of that location to 0x, say 2a. Okay, that part is just random. Okay, the 2a is completely random. When you look at the left-hand side of this assignment operator, 0 is 0, but I'm not using it as an integer. I'm casting that to a char pointer, and then I'm dereferencing that. In other words, I'm trying to store the byte, the content, the value, 2a, into location 0 of the computer's memory. Okay? So we'll go ahead and try this program out. In fact, we'll go into the debugger to see what happens when you try to run this program inside the debugger. So segfault.c, gdb, segfault, and just run the program, and it says program receives signal. Okay, signal is one of the concepts that we will talk about in this class, but for now we'll just say that the operating system objected. Okay, it objected this operation, and it said it's a segmentation fault. And the debugger is extremely helpful in this case because it's not just saying that your program tried to access a location that it is not supposed to. It even tells me what is the line. Okay, what is the line number that is offending these locations that is not supposed to access. Are we doing okay so far with this program?
That's pretty nice. That in general, it's kind of hard to get that information where.
That's because we're usually not running programs inside GDB. In other words, if I run segfault from outside of GDB, it just tells you segmentation fault. It doesn't tell you where the problem is. But when you run it inside GDB, GDB receives the segfault signal, but it also knows how to map that memory location back to the line numbers. So that's why it can give you a lot more information and say that, hey, this is the problem happens here. Yep.
I assume that it also executed a line, and then the kernel said, oh, no, you don't. And so it knows what line it was on already, no?
It attempted to execute instructions for that particular line, but in doing so, it caused a segmentation fault. In other words, the processor combined with the operating system actually knew the location of the instruction that is offending. And from that location, GDB with the debug information inside the object files can then look up the table and say, oh, okay, this location of this the location of this instruction maps to that line of that source file. So that's why it can tell you, when that problem, where that problem happens. Now, obviously, this program is extremely simple, and it's easy for you to figure out, where it happens. In the case where you have, 20 levels of subroutine calls, and it's the last level of subroutine call that's causing a problem, GDB can actually tell you who calls whom, calls whom, calls whom, calls whom, with what parameter until it gets to the subroutine that actually has the problem. So you can use GDB to track down problems far more effectively than using printfs and other techniques that you might be used to in your other classes. Okay. Does anyone know how to do that? Track down the levels of subroutine calls? No? Okay. Neither do I. I know they can do it. I just cannot remember the command to do it. So we'll go ahead and do an experiment here. And we'll say help. Help gives you a list or classes of commands that you can examine. In this case, I would say help data. Examine the stack. How about help stack? Help stack, backtrace is what it is. Backtrace. Now this program has a very boring backtrace because the main program is where the problem happens. On the other hand, if main calls F, F calls G, G calls H, H calls I, and so on and so forth, it will display not only main, but it will display all the different levels of calling. If you have parameters, it also shows the parameters. And that is a very, very useful tool for debugging because now you know how you get to a subroutine. That subroutine may be called from 20 gazillion places, but using this tool, you know exactly how it was called when your program failed. And it's an extremely useful tool. All right, but I kind of digressed here and started to talk about debugging techniques and not really focusing on privileges. But it did demonstrate the fact that your program, my program, the application program, could not change location 0. It could not read location 0 either. If I tried to read it, it would have done the same thing, segmentation fault, and say that I don't have access to it.
Would that have still happened if you were root?
If I were root, I think the same thing would still happen because a normal program does not have access to all locations. The root basically gives you extra privileges in terms of accessing files, but in terms of memory access, it is still confined by what the kernel thinks is appropriate for a particular program. You have to get into the kernel in order to have more flexible access to memory locations. Yep.
So in Windows 98, that program would have ran no problem.
Oh yeah, in Windows 98, that program would have ran and nobody would have complained anything. It's just that some other programs, could be the kernel, could be something else, that relies on location 0 would not do any, would not behave correctly anymore. Yeah. So that's why it was so easy to crash earlier versions of Windows before they used the Windows NT kernel, as the core part of the operating systems. These days, I think XP was the first non-commercial operating system from Microsoft that made use of the NT kernel. Before that, they had Windows 2000, Windows NT itself, 3.5, and then version 4, but they were not intended for end-user desktops. They were intended for servers and more professional deployment. All right, so are we doing okay so far with, it is good to restrict access to resources of the computer. But what if you're an interrupt surface routine? What if you're in an ISR? Do you think an ISR, an interrupt surface routine, the code that executes when your hardware input-output device needs attention, do you think that particular program may need access to, let's say, input-output devices? It probably does, right? Because when your hard drive, when your keyboard controller, okay, we don't actually have keyboard controllers anymore because we have USB, but let's say we have a keyboard controller. When your keyboard controller says, okay, somebody pressed a key on the keyboard and here's the key code, okay? What do you think the ISR has to do at a minimum? Clear the code, right? Read the key code, and that usually will automatically clear the source of the interrupt. But that operation means you'll be reading from an I/O location, an input/output location, that a normal application that I just wrote, would not have access to. Okay, so that means when we execute an interrupt surface routine, we need to elevate the level of privileges so that the ISR can do what it needs to do. Okay, but you also remember the ISR is kind of like a subroutine. When it's done with what it needs to do, what happens next?
It goes back to where it was before.
It goes back to the code that the hardware interrupted, right? So do you want that elevated privilege level to stick, or do you think we should resume back to the lower privilege level?
The lower one.
We have to go back to a lower one, okay? And that makes sense. And all of this stuff actually happens automatically. Okay, your ISR doesn't have to do anything special. The elevation of privilege level is automatic, and as is the downgrading of the privilege level. So all of this stuff is already done by the processor. The i386 processor internally has the capability to do all this stuff already. Yep.
Just remind me real quick, the interrupt service routine, where is that located or what?
It's just inside the kernel program space somewhere, and the
it's related specifically to whatever interrupt that is.
Right, and usually depending on the architecture, most architectures have a lookup table at a fixed location, and the lookup table is just really a table. Okay, you look up location 80 in hexadecimal, it gives you a vector to point out where is the subroutine to handle that particular interrupt. Okay. So are we doing okay so far with privilege levels, the necessity of it, and why the hardware capability to handle interrupts already makes you of it. Okay, so this is already done with interrupts. The next concept that we should talk about is our system calls. We have done system calls already. Yep.
I'm sorry, how does the hardware need to support privileges? It seems to me like an entirely software concept.
It requires hardware support as well, because if you run it at a low privilege level, because most of the time the computer is actually running user programs, not the kernel code or ISRs. So most of the time when an interrupt actually happens, it's doing something in a user program that has low privilege level. Okay, so here comes the interrupt. Okay, the hardware device says I need some attention. It changes the level of the interrupt line. Okay, in terms of hardware, it changes the level of the line. And then the processor interprets that line and go like, oh, okay, when I'm done with this current instruction, I have to figure out how to process that interrupt. Between that point and the time when the ISR actually gets control, when you continue execution in the subroutine, in the ISR, that's all hardware doing it. There's no software between the interrupt happening and the time that your ISR actually gets control. So all of the things that have to happen between those two events, they have to be done in hardware, not in software. And that includes saving the program counter of the user program on the stack, changing the privilege levels, and a few other housekeeping stuff before software once again has control inside the ISR. Yep.
So then basically, if I'm not mistaken, there's software on the hardware that's doing that. Is that correct?
The processor internally has silicon to specify the behavior. Yeah, you can call it microcode. Most people call it microcoding, which means there's a tiny little engine inside your Pentium processor that can that Intel can program, but you cannot program the microcode. Some processors allow a certain degree of flexibility even when it comes to microcoding, but most processors have it already hardwired by the time the chip is released. Any other questions? Did I address the question?
More or less.
What is the last part?
Well, it's specifically, I'm wondering about the privilege concept being supported in hardware. It certainly could make sense from an efficiency standpoint for hardware to handle it, but simply the execution of or the enforcement of privileges seems like something that could be handled entirely in software. So I'm wondering why hardware. It sounds like hardware supported it before software did, and I'm wondering.
But it cannot be enforced in software entirely, because if it could have been supported in software, then it can be broken in software as well. The whole idea is you're protecting the system from either malicious code or careless code. So that has to be done in hardware.
Okay.
Yep. All right. So now we are on to system calls. We're going from interrupts, privilege levels, and now we're going on to system calls. What exactly is a system call? We have done system calls already many times. I just never refer to that as a system call. Okay, that's a system call. Your read function that you call is actually a system call, because what this is instead of, does everybody know how the linker resolves symbols and just say, so you can have multiple files containing different subroutines?
I forgot. I forgot.
You forgot. Okay, so we'll go through that first. Okay, so what I'll do is I write a program that has two source files, and then the two source the linker has to link the two source files for the program to work as one single unit. So we'll go ahead and write a program just like that. So we'll go ahead and say this is f.c because it defines function f. All it does is to use stdio. Now, technically speaking, it is best to also have a f.h associated with it, so that the other program can refer to the header file to know what is in f.c. And what it does contain is just a void function f, which doesn't take any parameters, and all it wants to do is to say printf I am in function f. Okay, that's all it does. Nothing really exciting. And then we go to f.h, and the minimum you have to do in f.h is just the prototype of function f, so that the other program can also pound include f.h and understand the prototype of subroutine or function f. Okay, but I'm just going to do this part too. So I'll say underscore fh. If that is not defined, go ahead and define it, and then we have pound end at the end. This construct, around the actual content of the header file, make sure that we can pound include f.h as many times as we want, and it's not going to cause problems. This by itself as a prototype is not going to cause problems. In other words, this is fine, because it's telling the C compiler exactly the same thing every single time. They're all consistent. No big deal. No problem. What is not fine, and also things that people typically put in a header file, would be stuff like that. Okay, struct x int I char j, and so on and so forth. It is not okay for me to replicate the definition of struct x multiple times, because then there will be duplicate definitions of struct x. So this mechanism using pound if ndef, pound if not defined, underscore f underscore h, is basically saying, if this is the very first time I get pound included, this will be true because underscore f underscore h will not be defined. So I will have to do whatever is specified from that point all the way to end if. The first thing it does is to define the macro. And the macros are defined from now on and throughout, unless someone has an undef, it will stay defined. So that means I will also go through this code exactly once. The next time I pound include f.h, it will check this condition, but guess what? Underscore f underscore h will be defined already, because I have already pound included this file once. So this macro will be defined, so the condition that it is not defined is going to be false. When that condition is false, it skips everything in here all the way until the pound end if, so I will not end up with a problem of duplicate definition of struct x. This is a fairly industry standard trick to make use of header files. I do not know whether they teach it in your C++ classes here. They do? Okay, but it's a very, very important aspect of actually using header files. Okay, so now that we have f.h defined, we'll just go ahead and call the other one main.c. So main.c would also do a pound include of f.h, because I'm going to call the other subroutine. And then we have main here. I'm not going to do anything fancy with main. All it does is to call f and return. All right, so now we have two programs. And we'll go ahead and look at both programs at the same time. Just like that. The top portion is our main program, which is the entry point of the entire program. The second part, or the bottom part, is f.c, which defines the subroutine f that main is calling. So now I have two pieces of programs, and they can be compiled separately. Okay, so we'll go ahead and I think I'll let this screen stay the way it is, and I'll use another tab to do the actual compilation. So I would use GCC. Now, we take a shortcut most of the time in this class and just use GCC-O, which means it creates the executable from the source files. But the proper way to use GCC is to use -C to only create the object file from each source file. Okay, so the proper way to do it is to use -C to only create the object file, and then use -G to include the debug information, and -wall if you want to to turn on all the warnings and whatnot. But in the end, each GCC line should only compile one file. So in this case, I'll compile f.c first, and then we'll go ahead and compile main.c. So now when I look at my files, I have two object files. I have f.o being an object file, main.o being an object file. But don't you think that at some point, it should either complain that f is not defined in main.o or somehow resolve it? We're not at that point yet. Okay, the compiler makes the bold assumption and say that, well, okay, let's take a look at main.c. The compiler makes the bold assumption when it's in compile mode and not in link mode. It makes the bold assumption that, oh, well, it's not defined within this source file, but I feel comfortable that somebody else must have defined it. So when you use -C, when you use GCC, it doesn't make sure that it is actually defined somewhere else, because it is actually saying that if it's not defined here, it must be somebody else must have defined it. Okay, and that's why the compiling did not cause any problems. There were no errors from GCC-C of both files. The linker, on the other hand, is the one that has to resolve the undefined symbols. So if you run the linker, which is also GCC, but in this case I use -O to say that I want to create an executable as the output, if I only give it main.o, it's going to complain. Oh, new input file. That is bad because I just destroyed that file.
Oh no.
Okay, -O, okay, the executable is main, and the input is main.o. Okay, there we go. Okay, but it still complains because what I'm telling the linker to do is impossible. I'm telling the linker, use only main.o as the only component, give me an executable that I can actually run. The linker goes into main.o and say that, but hey, there's something wrong here. I don't know who defines subroutine f. And so the linker complains and say, there's an undefined reference to f, and it even tells me which line it is at, so that I can actually go to that line and go like, oh, okay, did I misspell that subroutine, or is it actually a subroutine that I have to include when I link it? Okay, so to fix this problem is pretty easy. When you actually link it, you just have to include the object file that defines, function f in this case, and the compiler is happy, and we are all done. Okay. So are we doing okay so far with the concept of sometimes we have to break up a program into multiple source files, and we will have to we have to compile each file separately and then link them all together at the very end. But Tech, what is the problem with GCC-O, and then just give it all the .c files as its parameters? It's not a problem with simple programs like this, or with any program that you will ever write at ARC or at any college or at any universities. Okay, because all it does is to recompile every single thing and then link at after it recompiles. How many lines do you think you would be writing in terms of your class projects here or at UC or CSU?
1,000 or fewer.
1,000 lines would be pushing it. That would be like a pretty long project. By most standard, it will be a pretty long project. How long does it take to compile a 1,000 line program?
2-3 seconds max. 3 seconds.
If you at the most, I think a fraction of a second. Okay, I would say that's a fraction of a second, even if you do it inside a virtual machine. Okay, it doesn't take that long. How big is the Linux kernel? In terms of number of lines, well, let's look it up. Let's look up the actual size of the Linux kernel. Linux kernel source number of lines. Okay. Statistics. Cool.
Somebody was just able to compile a full version of Linux kernel in 60 seconds.
You can customize the kernel in certain ways. Is it a full-up kernel?
It was a full stock kernel. It's just Intel's new chip. They don't have.
Oh, okay. Does it glow?
After it compiled that.
Yeah. Well, yeah. I'm not going to get into. I'm not going to get sidetracked here. But there are interesting stories of early Pentium processors and compiling Linux kernels. Okay, I guess I cannot stop myself anyway. Okay. I think this is back in the Pentium 3 or Pentium 2, one of the earlier Pentium processors. In Windows, everything works just fine, not a problem. But whenever someone uses the make to try to compile a Linux kernel, the computer will reset itself. Okay, and we're thinking, but why? I mean, GCC is a very stable tool. It has been well tested. In fact, it has been tested by processors before the Pentium processor. Say the 386, even if it's slow, it works, okay? And the Pentium processor is supposed to be backward compatible with the 386 family of processors and the 486 and so on. So what is the problem here? How come the computer would reset itself? And then later on, they found out what the reason was. That particular Pentium processor has a bottleneck. One of the ALUs, or one of the arithmetic logic unit, was a bottleneck. Everything has to go through that, for certain types of operations. And as it turns out, GCC, or the code of GCC, makes heavy use of that particular part of the processor. And in the end, it just overheats. It was just an overheat problem. Recompiling a Linux kernel overheats the processor, and just that part of the processor enough for the processor to die, and then the machine just kind of blacks out and restart from the beginning. You can look it up. I'm not making this up.
The question is, was this an intentional design decision where Microsoft said, we could really stop Linux dead in its tracks if we got Intel to do this?
Well, I don't think Intel really cares, about this stuff one way or another. I think they just did not design the processor appropriately and left a critical path, and did not have sufficient heat sinking, or design the transistors in a way to spread out the heat properly. But it was interesting. This is actually true. I mean, you can compile the Linux kernel and break a computer. Okay, but here we go. We have the number of lines of code, and this is not even up to version 3 yet. Not even 2.6, 30 something. This is 2.6.227, which is a little bit aged, a little bit older version of the kernel. And you can see the number of lines in the source code is up close to 9 million lines of code. Okay, how long do you think that would take?
One file, no problem.
To recompile 9 million lines of code is going to take a while. Okay, not only because the compiler needs to work, but also because when we compile a kernel, we turn on optimizations. Okay, we specify -02, -03, uppercase O, and that turns on optimization. Optimization means the compiler will look very closely at your code and say that, oh, this variable is assigned a value here, but we access that value here, here, and also here. So maybe I should keep that variable in a register so I don't have to reload it from memory over and over again. Oh, but wait, there are 20 other variables that this particular subroutine is also using, and now which one should I keep in registers and which one should I kick out of registers at what time? That's optimization, and optimization by its very nature is an NP complete problem, which means it's actually inherently a hard problem to solve. So when you turn on -02 and -03, the compiler takes a significantly longer of time, more time to compile, because it has to do all these things to optimize the output of the program. If you compile a Linux kernel with my Q6600 quad-core processor using the Core 2 technology, recompiling a Linux kernel typically will take an hour or two. I'm not kidding. It takes an hour or two. Okay. So imagine that you are a developer for the Linux kernel, or something similar in terms of complexity. every time you make a change to your program and you want to test it, go watch a movie. When you come back, maybe it'll be done. You test it, a little bit. Oh, darn it! I forgot to make another change. Make that little change. Go out and watch another movie. Right? Because each time you recompile, it's going to take 2 hours. Okay? How do we get around that problem?
Separate files.
Separate files. Separate the compilation from the linking. Okay? So that's exactly what I just did. Was I compiled the first source code. I compiled the second file. If I make any changes to F, I only have to recompile this guy here. I don't have to touch the other 7,000 source files. Okay, I do not need to recompile the other 7,000 source files. I only have to recompile one out of the 7,000. Okay, and that speeds things up a lot. But what about the linking? Doesn't it still have to link 7,001 object files in this case? Yep, but the linker runs a lot faster than compiling. Because one, there's no optimization when you're linking. And the linking process, for the most part, is bound by I/O speed. In other words, it's bound by how fast can you read the object files and crank out the output file. It's not, because resolving the simples is quick, easy. Okay, so linking is not a problem. Even if you have a huge program like the Linux kernel, the linking part takes literally seconds at the most. It is the compiling part that takes a long time. So that's why people always do something like this out in the commercial world. They always use multiple source files to try to control the remake time. We call this the remake time because when you make, it will only have to recompile as many files as necessary and then relink to create the updated object executable file. So are we doing okay so far with the concept of multiple source files and the linker? The job of the linker is to resolve all those symbols. We doing okay? All right. What about stuff that we need? Okay, right here we have stuff that we define. Okay, main is my entry point, and function f is also one of my own subroutine. So it makes sense that we can arrange things like this. But what about something that you need to rely on the operating system on the operating system for? In other words, what happens when you refer to read in your own program? Have we used this before? Just about every program that we have written up to this point has read, right? So what happens when you refer to read? What about the linker? What does the linker do when it comes to read? Well, yep.
Map it to a software interrupt, I would guess?
It actually calls a stub function, which is just like 3 or 4 instructions. Okay, so what it does is it will read is an entry point to a subroutine. Okay, and I can tell you what it looks like. So I'll just go ahead and say read.c. Read has its own source file, but it is really simple because what it looks like is something like this. It will be written in assembly. Okay, and what it does is and then we'll do some really kind of funky stuff. Maybe I'm trying to do some counting here. I think that's 12. You don't have to write this down. This is not assembly language programming. And those of you who took assembly language programming from me should still have some recollection of this. Really.
I was just thinking, is it bad that I don't remember what he's doing here?
Okay.
I remember.
That's read. Okay? So whenever you want to read some bytes from a particular file descriptor, that's the actual implementation. Okay? The linker will link with libc or the C library, which contains an entry point like read, and it is most likely written entirely in assembly simply because it is so easy to do entirely in assembly. So why bother with C when you can do it just like this in assembly? So how do you think 5, 6 instructions in this case can possibly contain all the logic to read from, can be a file, can be a socket, and so on and so forth?
It can't. It doesn't have to though.
It cannot. It doesn't have to. The magic has to do with this instruction here. Okay, the int instruction in assembly is basically a software interrupt. Okay? In other words, we are not really calling a subroutine in this case. What we are doing is we're setting up some registers, and then we execute a special instruction. And what that special instruction does is it's doing the same motion. It's going through exactly the same motion as a hardware device saying, you know, I need some attention, and pulling the interrupt line, except this time it is completely internal to the processor. There's no, you cannot observe anything from the outside. There's no interrupt line, there's no actual I/O devices, but it goes through exactly the same motion as an interrupt. In other words, when this instruction, let me refer to the line number here, when line 6 executes, which is a single instruction, what the processor would do is it will do exactly the same thing as if a hardware interrupt happens. In other words, it will save the return address, it will save the current privilege level, it will look up the vector, you know, to know where it is supposed to go. In this case, the vector is actually, you know, 0x80, which is 128 in decimal. So that tells it, you know, which vector point it should use to branch to a subroutine. When it gets to the subroutine, the privilege level will be elevated, and then it will execute the code specified over there. Okay, and that's where the complicated code will be located, inside the kernel of your operating system. When the kernel is done doing whatever it needs to do, it will go through the same motion as returning from an ISR. In other words, it will resume your privilege level. It will use the stack to remember where it's supposed to go back to. In this case, it will go back to line 9 here to actually return from this subroutine. Okay? But that really helps because when the kernel needs to read from a file descriptor, do you think the kernel can operate at the same privilege level as your application program? No. It needs elevated, you know, privilege levels in order to access the internal file descriptor table and a whole bunch of other stuff. Okay. All right. And so we have just solved that problem. We have solved the problem of, you know, how do we get the operating system to do what it needs to, but at the same time make sure that your application stays at a lower privilege level and the kernel has a higher privilege level to do what it needs to, and the returning of the lower privilege level is automatically done. So the hardware interrupt concept is now borrowed by the software interrupt instruction in order to get the operating system to do what needs to be done. Are we doing okay so far with this concept? Okay. So now we'll go ahead and do something else. Let me go back to the notes first to basically just, you know, explain, you know, where we are at in terms of the notes. This stuff is really hard to test. I'm not going to give you concept tests in this class. But then we're moving on to signals. Okay, and signals is kind of a difficult concept to understand from a certain perspective, but since we have talked about interrupts already, it is not that hard because it is related to interrupts. So before we move on and actually talk about signals, I will do this little demonstration. And the demonstration is to use the DD command. Okay, DD command, if you remember, do you guys still remember the DD command? We use it several times for, you know, various things, and I illustrated how dangerous this command can be as well. Okay.
This destroyer.
It can destroy disks, yes.
That's what DD stands for.
Yeah.
Oh, is that
That's the joke, is that's what it stands for, is disk destroyer.
disk destroyer? And then there's another command called DD rescue. I'm not sure this live CD doesn't have it, but DD rescue will go through your hard drive and try to rescue components, you know, sectors and stuff like that. All right, so we have DD here, and I'm going to specify something that is safe but not so smart. Okay, so I'm going to read from the input. The input is coming from the 0 device, which is an endless stream of the 0 byte. So there's no end to it. Okay, and the output is null, which is a black hole. So we just connected a white hole to a black hole using a wormhole.
So can you use dev null as a input? Or?
I do not think no can be an input. I think it can only be an output. It's a sink, it's not a source. 0, on the other hand, is always a source and never a sink. Okay? So this program doesn't do any harm, but it's not particularly smart either. Yep.
Don't you need to be root? Don't you need to be root to use DD?
I do not think so. It depends on what you're reading and what you're writing.
Okay.
You can use DD as copy if you want to. It's just that you have to type a lot more stuff than usual. Okay. So we'll go ahead and run this command. It doesn't really do any harm. The processor will be very busy at this time because it's just, it's just pulling stuff out of an endless stream and dumping into a black hole, and it disappears, right? But no harm is done. Okay, no harm is done. And then I want to find out how fast it's dumping stuff. Now you can type Control-C and stop the program, and then it will tell you that in the past 20 seconds or so, it has transferred 17 gigabytes of zeros from the 0 device to the null device. Very helpful. Good job. Yes. All right. And it is doing it at 829 megabytes per second. Now that's a really good speed. I mean, it's almost up to like the gigabytes per second. Wow. Okay, very cool. But what if you're doing something like this and during this process, you want to find out what is my current transfer speed so that I can anticipate when it's going to be done? In other words, what if this command was actually constructed and say that this is actually the file corresponding to the image of a real hard drive, and this is an actual hard drive like SDA, SDB, and so on. And what you're doing is you're restoring the image on the hard drive at a bit-by-bit level. You're ghosting. You're basically reversing the ghosting process to clone a hard drive. Okay. So you might want to know how fast things are being done, so that okay, I know this is going to take another 2 hours. I won't be back until this is done. Go out and watch a movie, right? Or recompile the Linux kernel.
As opposed to Microsoft, which just puts random times up for the next step to
Yep.
be done.
Yep. Well, this stuff is more predictable because it's just bound by the I/O efficiency. So how do we do it? Well, let's see if we can do it this way. Okay, I'm going to open up another tab here. And in this tab, I'm going to use a command that seems pretty dangerous. Well, first of all, let's do this first. This one, ps-cdd, ps will give you a list of all the processes. In other words, all the programs that are in execution can be listed by ps. But in this case, since I did not specify -af and all the other flags, it will only show the commands that I personally ran in the background that is active. And DD is one of those programs. It has run for 1 minute and 12 seconds already. I'm using PTS. It's a pseudo teletype terminal, number 2, and the process ID is 4069. The PID, or the process ID, uniquely identifies a particular instance of a program running. Remember, a process is like an object, where a program is more like a class. So a program sitting on your hard drive or your live CD ISO is not going to do anything. It's just taking up space on the hard drive, but it's not taking up space in terms of the memory of your system. When you run the program, it does consume resources. It takes up processing time, it takes up memory space, and so on and so forth. So right now, I only have one single instance of DD running, and the PID, the process ID, is 4069. So I'm going to do something that seems to be dangerous, kill, and I would say USR1 minus USR1, and then specify the process ID. If I did not specify -USR1 and just say kill 4069, it would have killed the program. Okay, but since I specified -USR1, let's go ahead and find out what happens here. Oh, this program just reported something. It told me that it is not done yet. It has copied 143 gigabytes, and it's copying at the speed of 837 megabytes per second. But that's weird. Don't you think that is a little bit weird? Because I ran this program, DD, on its own, in its own terminal, and I ran the kill command in another terminal. So how does this has to do with the DD command spewing out this stuff while the program is actually continuing to copy stuff from 0 to null? I can do this again. And once again, DD responded and say that, oh, by this time we have 186 gigabytes copied, and the current average speed is 836 megabytes per second. What is going on here?
Well, you use the process ID.
Mm-hmm.
Do you not have the privileges to kill it?
Well, I can kill it if I want to, but I did not want to kill it. I want to find out, how fast it's copying, how much is copied, so I can kind of anticipate how much more time I need. Yep.
I never understood how to use it until now, but I know that a major component of what kill does is it is essentially a call or a program that sends signals to programs.
Exactly.
I never knew what that meant until now.
Yep, it's using signals. Okay, so let's just say that I am the DD program doing something that's completely useless, right? I'm just copying. There was a mosquito. It's over there now. They like me. I'm the Twinkie. I have the cream filling. Yeah, it's bad. Whenever I go camping, other campers like to sit around me, because as long as they sit around me, the mosquitoes always prefer me. I can put insect repellent on. If I miss one spot, they will get it. They will know which spot I missed and then bite me there.
They say that means you have good blood.
No, I've heard it's got a really high metabolism.
It's the carbon dioxide. They can detect the concentration of carbon dioxide. They actually go after the grill too. They think the grill is a person and is putting out a lot of carbon dioxide. So the grill sometimes saves me. And after a while, working with the grill, I smell like the grill too. All right. So what is happening here is, let's say I am the DD program in execution. I'm process 4069. Okay. So I'm busy moving stuff around in an endless fashion, right? And what happens is let's say you are the kill command. Okay. And what you're doing is you're actually sending me a signal. Okay. Sending someone or sending a process a signal is really just saying, hey, dude, okay? And then you put up a number, okay? In other words, there are different signals you can send to a process. And the signals are identified by a number, nothing more than a number. In other words, sending a signal to a process is nothing more than sending a number to that process, okay? And USR1 is just a particular number. If I want to look it up, I can find out exactly what number it is corresponding to. Man, kill, and if you look at USR, I guess not. Specify the signal to be sent, list. Okay, there we go. So kill-L, you can see, where's USR? Right here. So USR1 is basically 10. It's just a macro definition. Okay, not macro, it's a symbolic definition. So it's the same if I want to say kill -10 4069. It accomplishes exactly the same thing, because USR1 is really just a number. Okay, so you're just sending a number. The kill command is nothing more than sending a number to a process, which we call a signal. But when I receive a signal as a program that's running, it's an interrupt. To me, it's an interrupt. Okay, it's like, oh, hey, tag, somebody wants your attention. All right, what? 10. 10 was the message. So when I look at that message 10, then I will look up, a table that I have, okay, that says, okay, tag, you can probably expect these signals to be sent to you, and for each one, this is how you're going to handle it. So when kill send me the signal 10, I look up my table and say, well, am I supposed to handle it? I guess so, it is in my table. And then I look up the table and it goes to a particular subroutine. It points to a certain subroutine. That subroutine will contain the code to handle signal number 10, the USR1 signal. Okay? Can someone guess what that subroutine may look like based on the output that you're seeing on screen right now?
I like display what you're doing.
Well, exactly. All it has to do is to look at the statistics of the command up to this point, print it out to, this is actually a standard error, which maps to the same teletype as standard out in this particular case. It will print it out, and then when the subroutine is all done, it just says, okay, return, go back to copying bytes from 0 to null, and just continue. Okay. In other words, it kind of resembles the whole concept of interrupts. Exactly. Except in this case, you or another program can control the interrupt. And it's definitely not a hardware interrupt, it's a software interrupt. And it is asynchronous. In other words, DD cannot anticipate when I will send it this particular signal. Okay, signal 10. Question? Okay. But other than that, it is really exactly the same as an interrupt. Okay, so this is a good time to kind of digress just a little bit for those of you who write code for microcontroller units in C. Okay, so I'm just gonna okay, let's see. I think I'll do this part here. Okay. It's just I want to illustrate. How many people know what is an MCU, a microcontroller unit? Nobody? Okay.
What happens if you send DD signal 9?
Then it would kill it. There are two kills, two kill signals. One is stop and the other one is kill. One is a gentle request and say, please die. And the other one is say, the other one says,
You have to say please.
the other one does not say please, and the other one is unstoppable. You can basically stop it and say, I don't want to die now. The other one says, the other one sends a knife. Okay, not a number. Yeah. Okay, so we'll go ahead and look up microcontroller, because I think at this point I can just kind of digress a little bit to talk about what about programming one of these things. A microcontroller unit is, or in short, MCU, or MUC. There are different names for these microcontroller units. It's basically a system on a chip. We're not talking about a processor. We're not talking about the RAM. We're not talking about the flash. We're not talking about the I/O devices. We're talking about all of the above, fully integrated into a single chip, into a single integrated circuit. And they're typically very inexpensive. Depending on what you want in one of these MCUs, the price of an MCU can go from half a dollar, 50 cents or so, all the way to possibly $50, $80 or so. But because they're fully integrated, they're inexpensive for the most part. They're very energy efficient. They're programmable, and most of the time they're programmable in C too. If they have enough resources to implement a stack, you can program these things in C. And they come in very handy. If you look into cars, okay, each car probably has, I think, about 10 of these things at least in a car, in a modern car. Engine control has one, anti-lock brakes has one, vehicle control, dynamic control has one, your AC system probably has one, your entertainment system has one, your airbag control system has one, and so on. Okay, some of these have operating systems. In other words, if you use an ARM-based MCU, they typically can run Linux. There's enough resources to run Linux. And one of the interesting ones you can look into, is it called Raspberry Pi? Raspberry.
Oh, you tell us about that on a USB stick?
Raspberry Pi, I think this is it.
Oh, yeah.
Yeah, so this is basically an MCU, but it also has the necessary circuit to turn it into a full-up computer. So we'll just go ahead and take a quick look at this one. Okay, this is it. Okay, 256 megabytes of RAM, CPU, and GPU on a single chip. I mean, that's all the resources that you need in order to run even a slightly modern, operating system like Linux. HDMI is just a connector. There's no chip here. I'm not quite sure what this chip is, but it's probably just a peripheral chip, so they can talk to properly to everything else. It could be a USB driver chip, so that you isolate the processor from USB signals. But nonetheless, this entire system is implemented by a single chip. There's no separate chip for RAM. There's no separate chip for flash memory. There's no separate chip for the processor, and there's no separate chip for the graphics card, and so on. It's all integrated into one single chip. And because of the mass production of this kind of chip for all kinds of devices, tablets, cell phones, and whatnot, the cost of one is really low. Now this one is lucky because it has all the resources that it needs even to run Linux. Okay, you can basically shrink Linux down to run in 256 megabytes. But when you look at something else like AVR, 80 mega, 32, this is a good one to take a look at. This chip, which is this guy here, is smaller, it's less expensive, but unfortunately you only have 32 kilobytes of flash space to put your program, and you only have, let's see, how much RAM do we have here? I think this one has 2 kilobytes of RAM. Yeah, somewhere around there, 2 kilobytes of RAM, and that's all the resources that you have. Can you run an operating system given that kind of resources? Nope. So there's no kernel, and because there's no kernel, no such thing as an operating system, there's also no I/O device, no drivers. There's no kernel, no driver, no operating system whatsoever. Whenever you write as your C code runs directly on the chip itself. You don't have file descriptors. There's no file system to support file descriptors. You cannot open a file. There's no such thing as a file system. So when you have a chip like this, and one of the signals or one of the I/O devices has an interrupt, who's going to process it? You. So you have to handle interrupts in this very raw form when you program one of these chips. And most people think, wow, that's going to be hard, right? I mean, in my entire college years, I have never been taught of how to do something like this. But you can actually do it in C. You don't have to drop down to assembly level, even if you want to handle I/O devices in an ISR, in an interrupt surface routine. And the way they do this is, guess what? Which concept in C programming do you think they borrow in order for you to specify your own interrupt surface routine? Signals. They use the same mechanism as signal handling in this case. Okay. So are we doing okay so far in terms of the concepts connecting interrupts, system calls, and signals? We doing okay? All right. So a signal is nothing more than a quote-unquote interrupt, and it has a number associated with it. Okay. And then there are these, commonly used signals. These two are the ones that we just talked about. Kill is 9, stop is something else. I cannot remember what it was. Okay, whereas this is kill, and 19 is stop. Okay, so stop is a gentle request and say please die, and kill is sending over a knife, a grenade. Okay, yeah, a program can stop. A stop may not stop certain programs. A program can choose and say, I don't want to be stopped. I want to keep on going. I want to do something else. But a sig kill will almost for sure kill a process because it is not blockable. Okay. Well, we have a whole bunch of other stuff too. We have USR1, which I think stands for user one. Term is terminate. I think that's the usual kill. Is term stop can be continued, so it's actually more like a pause. Okay. Are we kind of doing okay so far with the concept of signals? Okay. So now we talk about how do we handle a signal? How do we, tell this program that I'm writing and say that if someone sends me signal 10, which is USR1, that's one of the quote-unquote programmable one. You can choose to ignore it, you can handle it, you don't have to quit because of it. Okay. So how do we specify that? First of all, we are going to have to define, we have to understand this type. So the first thing we have to do is to kind of go back in C and C++ programming and make sure that we understand what this line really means. What does it mean? It's a type-def line, so we are defining a user-defined type. The name of the type is sig_handler _t. That's the name of the type. But what exactly is it? How many people have seen the name of a type inside the parentheses with an asterisk in front of it?
Isn't this
function.
Isn't this a function that takes an int and returns a pointer to sig_handler_t type?
Well, the type itself is a pointer to a function that returns void but takes an int argument.
Okay.
Okay, I'll say that again. The type, which has a name of sig_handler_t, is a pointer to a function that returns void, but the function takes a parameter of type int. Okay? So what you need to do is to define your signal handler using this convention. This would be a good shell for a signal handler, because what is handler doing? Handler has a return type of void. It matches the return type of sig_handler_t. It also has a parameter type of int, matching the parameter type of t int in sig_handler_t as a type. Okay. In other words, you can define your signal handler just like this. Pretty easy. Okay. It's a function that returns void. It takes an integer parameter. That's it. Are we doing okay so far? How to write a signal handler, which is actually analogous to a interrupt surface routine, except in this case it handles signals and not interrupts.
So do you need to set that up any further, or is that basically you have that, your type def, and then you just...
The type def is in the signal header file already, so it is already predefined. As long as you include the signal header file, it will have it.
So any function you make with that signature, that setup is gonna be...
Nope, you have to use another call to tell the operating system and quote-unquote register your signal handler.
Okay.
Because by default, when you start a program without setting up your signal handling, by default, it only has a certain set of handling capability. It will say, if someone send me a sig term, I will die. If someone send me a sig kill, I will die. But it will not process or handle any other interrupts. You can send it you can send it USR1 or signal 10. It just ignores it because it has not told the operating system that it has the ability to handle that particular signal.
This is related to the B select, right? I think it had some signal.
Yes. Yep. It is related to that because when you can set up a timeout, you can, at the end of a timeout, it can generate a signal to basically quote unquote wake up a process and say, hey, dude, got something for you. So that's why it is related to that. Okay. So the next section 7.3, talks about how do you specify the disposition of a signal. And this one is kind of confusing because there's a function called signal that tells the operating system how you want to handle a particular type of signal. So signal as a function is this, in this context, this signal is the name of the function. This is the prototype of the signal function. And what it does is you have to tell it what signal you're dealing with, let's say 10 for ERS-R1, and then you have to tell it how to handle that particular signal. Okay? And there are special things too, because what you can do in your program is you can change the way you want to handle signals. It doesn't have to be specified once and stay that way forever. In other words, in certain parts of your program, you can say, I'm at a critical part here, saving a file. I will not terminate just because the operating system tells me to terminate. I want to finish saving the file first. So you can change the handling of sig term during that part of your program or the execution of that program. When your program is not at a critical point, there's nothing to save, nothing is really in progress, you can revert it back and tell the operating system and say, oh, we'll just go back to the default way of handling sig term, which is to actually terminate a program. Yep.
I may be getting way ahead of us, and feel free to stop me if I am. But if you're essentially processing this signal with a function that is only past the signal number, how do you read the state of the rest of the program without global variables?
You have to rely on global variables.
Okay.
But then you have to be very careful
Okay.
because the interrupt or the signal can happen at any time. It's not going to happen between C statements. It can happen within C statements. Let's think about this a little bit here. Okay, so let's say
That's nasty.
it is extremely so. Okay, so you guys now start to understand, why it is kind of nasty to have to deal with MCUs, microcontroller units, when you don't have an operating system, because interrupts can happen at any time. So let me see what is the best way to do it.
So they happen between processor instructions, but not necessarily between C instructions.
Correct.
Oh man.
Okay, let me just use a VI to give you an example. Okay, so this is non-atomic. I just call this non-atomic. Now, see, to illustrate, what is non-atomic. What seems to you as atomic is not atomic to the system at all. Okay, it's very, very simple. Okay, main. Okay, in main. In ij. Okay, I gets j. That's not atomic. That is not an atomic operation. I gets j is not an atomic operation. In other words, a signal can happen within that particular assignment operator. I know that for sure because the I386 instruction set does not allow a single instruction to move or to copy from memory to memory. So it has to be broken up into two different instructions. Okay? So let me just kind of comment here and say that this instruction or this line is, typically, it breaks up into two move-long instructions. The first move-long instruction is going to move, some displacement. I'm going to say -4 here, EBP to a register, and then it needs a second instruction to copy from EAX to -8. ESP, or something along that line. Okay, the exact displacement from EBP is not important, but the important part is it is actually implemented in two different instructions. And guess what? The signal can happen here. Okay, a signal can happen here. Okay, in this case, it's not a big deal because we haven't really finished up the operation. So either I has the old value or it has the new value. It cannot be in between. Okay? Well, I can make the in between happen pretty easily too. Struct x int ij. So if I change my program to refer to struct x ab and change this part here to a equals b, which copies the entire structure b to a, you can see how it might have copied just member I but not member j yet, and then the signal happens. Okay, and that can get very tricky because if you have a data structure, a circular queue, a stack, or whatever you want to deal with that is a complex data structure, when the signal happens, the structure itself may not be self-consistent because it is actually in the process of updating itself. You might have updated one part of it, and then the other part has not been updated. So when you look at the structure as a whole, it is not self-consistent. Yep.
So do you have to check consistency of state before you can rely on your state in an interrupt?
You can turn off signals for a certain amount of time. So basically, you can define your own atomic operation by saying, I will not handle signals at this point. Do everything that you cannot afford to have interrupted. At the end of that, you just re-enable signal and say, okay, now I can handle signals again.
Okay.
That's the only way to get around problems like these.
Would it hold any signals that you receive?
Yes,
during that
yes,
time?
it will. The operating system will hold off the signals until the process or
Then you would
the
get them
process is
after-
ready.
Then you would get them after you started
Right.
them.
Yep. Okay, so let's go ahead and write one single program to handle, USR1. Okay, just like DD. And I think it's probably a good time to stop DD now that it has copied 1.4 terabytes. Wow, very good. Okay, so we'll just write one little program. I'll just call that signal demo, and we'll go ahead and say void USR1 handler, and we'll just use bprintf to standard error, which is 2, and say got an USR1 signal, just like that. And then in my main program, what I need to do is to use the signal call, the signal function, to register the fact that I am using this subroutine to handle that particular signal. So I would just have to say signal. I forgot to include the signal.h file, and to signal is just signal.h. Okay, that's pretty easy. That's my editor right here. Signal 10, which is USR1, and then you just say USR1 handler. So this is how you pass a pointer to a subroutine in C. And now include signal.h, that. So this call doesn't really do anything. All it does is to tell the operating system and say, hey, this process now knows how to handle signal 10, which is has a symbolic name of USR1. And then I'll just do the really smart thing here. Get myself into an infinite loop.
I think GCC may complain with the right options.
With options it will, but without options it does not.
GCC-P down.
Stop nagging. Okay, in function parameter name omitted. Okay, so I have to give it a name. Okay, just not going to use it though. All right, so now in one of my other process, I'm going to say ps-c sigdemo, which is the name of the process. Now I can see the PID or the process ID is 4594. So I can say kill-USR1 4594. Go back to my program that has a tight loop, and it went into the subroutine, print that little message, and then it return back to the infinite loop. If I had anything like printfs or whatever in the infinite loop, it would have kept, it would have just kept going. It would have continued the operation after it printed this message. Yep.
The int that you received would have been a 10 now, right?
Yes.
Okay.
And you can do it again and again because this signal is not causing any harm. So the program, every time it gets the signal, it goes into the subroutine, execute whatever is in USR1 handler, and then returns back to the original point and continue execution. Okay. Now signals can be, this doesn't seem to be very useful, but later on we'll talk about how signals can be very useful, because when you set up a timeout period using, let's say, select and some other calls, you can actually set it up so that when the time is up, it does not just return it actually sends the process a signal. Okay, and then you can use the signal handler to deal with the timeout conditions and whatnot. So this is the end of today's lecture. We did get into a little bit of programming today, using signals, but it is very important for all of us to understand the concepts. Okay, going from polling to hardware interrupts, going from hardware interrupts to system calls, going from system calls to signals. So those are the concepts that we talked about today, as well as the practical use of signals in this case. All right. So I'll see you guys on Monday. Have a nice weekend, and work on the homework assignment.
It's due on Monday?
I think someone told me that I used the wrong time to set it up. So it is, I made it so that it is due on the 26th, which is Monday.
But your verbiage in there says it's due after spring break.
Oh, inside the assignment?
Yeah.
Oh, okay, I see.
So it is due on Monday.
It is, well, it's due on Monday, but if you,
Yes, I'm listening.
Is it supposed to be on spring break right now?
It's towards the end, I think it's like the second paragraph from the end.
Yeah, it says the Monday after spring break, but.
try to get it done, on Monday.
Okay.
Try to
I
get it
will.
done on Monday. Yeah.
I'll
That's
do my best.
that's permissive parenting right
I
there.
love it.
And how'd that work for you today?
Yeah.